In this presentation, we examine the precise mechanics of paint drying at a molecular and physical level. Over the next 2 minutes and 55 seconds, discover how liquid coatings transform into tough, protective films through evaporation, particle coalescence, and autoxidative cross-linking. Paint is a carefully engineered colloidal dispersion. Its performance during and after drying depends entirely on the interplay of pigments for color and opacity, polymeric binders that form the continuous film, solvents that provide the necessary fluidity during application, and additives that fine-tune stability, flow, and drying behavior. Water-based latex paints suspend submicron polymer particles in water, while solvent-borne and oil paints use dissolved resins or drying oils in organic carriers. The drying mechanism is fundamentally dictated by this formulation. All paints begin drying by losing solvent to the atmosphere. This mass transfer process follows well-understood physical principles. Surface molecules escape when they have sufficient kinetic energy. Airflow maintains the vapor concentration gradient by removing the saturated boundary layer. In thicker films or later stages, diffusion of remaining solvent through the developing polymer matrix becomes rate-limiting, following Fick's laws. High relative humidity dramatically slows water-based paints, because it reduces the thermodynamic driving force for evaporation. Once 50 to 70% of the solvent has left, the surface skin raises the glass transition temperature, making the final stages of drying disproportionately slow. Traditional oil and alkyd paints cure chemically through autoxidation. Atmospheric oxygen attacks the unsaturated double bonds in the fatty acid chains of drying oils such as linseed or tung oil, forming hydroperoxides. These decompose into free radicals that propagate a chain reaction, creating covalent cross-links between oil molecules and building a rigid three-dimensional thermoset network. Temperature, humidity, film thickness, airflow, substrate porosity, and formulation details all interact in complex ways. Lower temperatures slow both evaporation and reaction rates. Thick films suffer from diffusion limitations. The transformation of paint from liquid to solid film is a sophisticated orchestration of physical and chemical processes. Understanding these mechanics explains why proper environmental conditions and following technical data sheets are essential for achieving durable, professional results every time.